In this presentation, I'm going to be describing the differences between covalent and ionic bonding, discussing the basis along with distinguishing between properties and the structures of both. To finish, we will also be covering many useful practice problems to further the understanding. By now, it should be quite obvious that chemical bonding is much more complicated than simply determining whether a bond is either covalent or ionic. Instead, there's a defined continuum to classify these bonds more accurately. The way we generally classify bonds is by using the electronegativity differences. Let me remind you that electronegativity is a measure of the tendency an atom has to attract electrons. As seen in the diagram, a nonpolar covalent bond has an EN difference of 0 to 0.4, with electrons shared equally. A polar covalent bond has an EN difference of 0.4 to 1.7, with an uneven sharing of electrons. And lastly, an ionic bond has an EN difference of above 1.7, resulting in the full transfer of electrons. Starting off with the basis of each, a covalent bond, which can also be referred to as a molecular bond, is a bond that involves the sharing of electron pairs between nonmetal atoms. This bond comes from the electrostatic attraction of the nuclei of both atoms. A covalent bond is formed when the bonded atoms have a lower total energy than that of the widely separated atoms. For a quick example, let's look at the bond between two hydrogen atoms and an oxygen atom. In this covalent molecule, the electrons are shared, and each atom has a full valence shell. As seen on the right, the EN difference is 1.24, therefore the molecule is polar. Before moving forward, let's recall what the octet rule is. The octet rule states that atoms tend to form compounds that give them 8 valence electrons, which is the electron configuration of a noble gas. Given a few exceptions, such as electron-deficient molecules, molecules with an odd number of electrons, and molecules with expanded valence shells, atoms want to have a full valence shell. The octet rule is important because it predicts how atoms will bond based on their outer shell of valence electrons. In the image to the right, we can see that each compound has a full octet. On the other hand, we have ionic bonding. This is the complete transfer of valence electrons between atoms. This type of chemical bonding generates two ions with opposite charge. This includes a metal atom, which gives away its electron or electrons, and a nonmetal atom, which accepts the electron or electrons. As seen in the bond between sodium and chlorine, the sodium atom gives away its single valence electron to the chlorine atom, resulting in both atoms now having a full octet and opposite charges. On the right, we see that the EN difference is 2.23, therefore it is ionic. Moving on, these bonds can also be differentiated easily because of their different physical properties based on the nature of their bonding. Beginning with covalent bonding, due to the sharing of electrons, they exhibit characteristic physical properties including high melting points and boiling points, low enthalpies of vaporization, compounds of soft or brittle solid forms, and poor electrical and thermal conductivity. Covalent bonds between atoms are extremely strong, resulting in higher melting and boiling point, because covalent bonding occurs when two atomic orbitals come together in close proximity and their electron densities overlap. However, low melting and boiling points occur in covalent compounds because of the relatively small amount of energy required to overcome the weak interactions between covalent molecules. So these compounds melt and boil at much lower temperatures than metallic and ionic compounds. The enthalpy of fusion is the heat required to melt a single mole of a solid under constant pressure. Low enthalpies of fusion or vaporization occur because the order of covalent bonds are usually one or more of magnitude smaller than they are for ionic bonds. Covalent compounds are usually soft and brittle solid forms because of the weak intermolecular forces that make the solid form of these compounds easy to break and distort. And lastly, poor electrical conductivity occurs because they do not have charged particles capable of transporting electrons. Covalent bonding can occur in single, double, and triple bonds. The strongest type of covalent bonds are sigma bonds, which are formed by the direct overlap of orbitals from each of the two bonded atoms. Single covalent bonds occur when one pair of electrons is shared between atoms as part of a molecule or compound. Double and triple bonds are comprised of sigma and pi bonds. Double and triple covalent bonds are stronger than single covalent bonds, and they are characterized by the sharing of 4 or 6 electrons between atoms respectively. Double and triple bonds contain 1 sigma bond and 1 or 2 pi bonds. Pi bonds are a result of 2 lobes of an orbital on one atom, overlapping 2 lobes of an orbital on another atom. Now we'll discuss some of the physical properties of ionic bonds. Some of these main properties include high melting points and boiling points, the formation of crystals, higher enthalpies of vaporization, hard and brittle structure, and the conductivity of electricity, but only when dissolved in water. Ionic bonds are held together by the electrostatic forces between oppositely charged ions. Since an ionic lattice contains a large number of ions, lots of energy is needed to overcome the ionic bonding, which results in higher melting and boiling points. Ionic bonds form crystals because the structure of crystals consists of many alternating positive and negative ions bonded together in a matrix. Since ionic bonds have high melting and boiling points, their enthalpies of vaporization tend to be 10 to 100 times larger than covalent compounds. Ionic solids are very hard and brittle. Hard due to the strong bonds, and brittle since when distorted, like-charged ions move closer to each other and the strong electrostatic repulsions shatter the crystal. Ionic compounds conduct electricity when molten, liquid, or in an aqueous solution, dissolved in water, because their ions are free to move from place to place. Ionic compounds cannot conduct electricity when solid, as their ions are held in fixed positions and cannot move. A few examples of ionic and covalently bonded compounds we see every day include table salt, sucrose, which is sugar, toothpaste, vinegar, and many more. Before moving forward, I briefly want to discuss the bond strength in ionic and covalent bonds. Covalent bond strength can be classified in terms of the amount of energy that is required to break them. It can be seen that double bonds are stronger than single bonds, and triple bonds are stronger than double bonds. Therefore, it would take more energy to break the triple bond in N2 compared to the double bond in O2. The strength of the ionic bond is directly dependent upon the quantity of the charges and inversely dependent on the distance between the charged particles. A cation with a 2+ charge will make a stronger ionic bond than a cation with a 1+ charge. In comparison, ionic bonds are generally stronger than covalent bonds because the electronegativity difference between the two elements is much greater than that of the two elements in the covalent bond. For the last few minutes of the presentation, I'm going to review some examples of chemical bonding and how to distinguish between the different types. Let's start with methane. Methane is comprised of 1 carbon atom and 4 hydrogen atoms. When calculating the electronegativity difference, we can see that this is a polar covalent molecule. Next, we'll look at lithium iodide. This one is a bit tricky because it is clearly a bond between a metal, lithium, and a nonmetal, iodide. However, when calculating the electronegativity difference, we see that it is in fact a polar molecule because the EN difference is 1.68, just below 1.7. Now for sodium fluoride, when we calculate the EN difference, we can see that this bond is obviously ionic because of the complete transfer of sodium's valence electron to the fluorine atom. Next, we have sulfuric acid, and after the calculations for EN difference, we see that this molecule is simply polar. In the case of dinitrogen, the EN difference is 0, so it is a nonpolar covalent molecule. However, we can classify this and the other diatomic elements as pure covalent molecules. Now we have carbon monoxide. This one is very simple as well, and when we calculate the EN difference, we can see that it is a polar molecule. Lastly, let's look at a harder to distinguish bond, hydrogen fluoride. HF is a covalently bonded gas at room temperature. The electronegativity difference between hydrogen and fluoride places the bond in a sort of middle area, which some sources will classify as ionic. However, the HF bond's electronegativity difference is 1.88, but it is considered polar covalent because hydrogen is a nonmetallic element. To finish off this presentation, let's decide which of the given molecules are more polar. To decide this, we can look at the electronegativities and decide which has more ionic characters. Firstly, between HCl and NH, HCl would be the more polar molecule because it is slightly more ionic than NH. HCl has a 0.12 higher electronegativity difference. Second, between NO and PCl, PCl is quite obviously more polar than NO because it has more ionic characteristics. The difference of En between both molecules is 0.57. That concludes my lesson on ionic and covalent bonding. I hope that you were able to learn more about distinguishing bonds and the bonding continuum. Thank you.